Everyone seeing a presentation at this point? Yes, good. Okay, so my name is Bjarte Hannisdal. I am in charge of this progress domain one of the domains of iEarth. And so I've been involved with the application process for some time. And if we think back to the earlier version of iEarth in the first round of the application, there was an ambition not only to change the way we teach earth science, but also the content or the curriculum, if you will. And the main focus was on this idea that there was a much needed shift towards a modern earth systems approach. And that was the core, essentially, of the original version of the Progress Domain 1, was to have an earth systems focus in teaching. And this is still very much true, and it's still an important goal and something we strive for, but that's in many ways an internal earth science issue. It's something that we do anyway, in many ways. And for the Center of Excellence in Education, there's another dimension that we need to keep in mind, which I'll talk a little bit more about. And so we still want to have this content revolution, if we will, in the back of our heads. But the way we want to achieve this shift, I think, has changed a bit over the years. And the final version of the iEarth project has changed a little bit in that sense. So I'll try to explain a little bit how and why that has happened. So there's not much information on the web page for now. There's the original blurb that was written quite some time ago, but it does have a sentence or two that gives away a few things. So it says somewhere that we want to sort of invite people to recast their discipline-specific teaching as instances of something more general. And that's kind of the key here. I would say, if we think back to some of the meetings we've had over the years discussing teaching, even strategy meetings discussing, the future of the department and that sort of thing, there has been a tendency for those types of discussions to quickly devolve into sort of, I don't want to be too cynical here, but it's kind of trench warfare between the different disciplines, right? So what's more important? Well, my discipline, of course, is very important. Therefore, we need the students to know more about that discipline. And then it's the other person's turn, and there we go. So if one of our main goals with iEarth is to build a collegial teaching culture and a culture for teaching discourse, it's key that we are able to keep that discourse at sort of a meta level, okay? Arguing about what disciplinary content is most important is part of that discussion, but it's probably not the way to go. And so we need to attack it slightly differently, I think. So if you look at iEarth, and this is one example of one of the mottos that we've thrown out throughout the years, clearly, we want to highlight that earth sciences are of vital importance. And this is relatively easy to do, and it's not particularly controversial. Nothing could be more important, arguably. And we like to throw this poster out there. Earth science is important to every aspect of society. Even paleontology is in here somewhere. So that's good. It's very important. We need students to know. And again, this is not controversial or something that we disagree about. But there's another dimension to this. And this has now become very apparent because it's both a bottom-up issue and it's also a top-down political issue. And that is the fact that as a higher education institution, we have to increasingly hold ourselves accountable for how candidates that go through our educational program gain the competencies that society needs. And that's something where we are not quite as good at being explicit about. And that's something that we probably need to think carefully about. So here's one example of one of these lists or of skills or general competencies that we are more or less asked to show that we provide our students. And there are many arguments for why we should do this. And there's also some pressure from teachers on a day-to-day basis to actually start working with this in courses. So that's where iEarth and sort of general trends in higher education and politics, if you will, converge to some extent. And this is where we need to think carefully about how we want to go ahead. I'm just going to show an example of a course that I teach just to illustrate how some of us are beginning to dabble with competencies in our courses, for better or for worse. And this is a relatively new course. This is the second time we're running it this fall. It's called Introduction to Geobiology. And it's an unusual course for the bachelor students in our program because it does things a bit differently than what they're used to. There are no lectures in this course, there's no textbook, and there's no exam. So many of the normal elements are not there. It consists of a bunch of learning activities where students work on, as far as possible, authentic problems. And then we try to assess them on how they work on these problems. So as an example, one thing they do in this course is they build Vygotsky columns, which is classic environmental microbiology experiment. And it's very relevant for geologists. So we have them build these, and then we add some fancy stuff like microscopy using smartphones. And we do optical measurements of oxygen concentrations inside the flasks. So we do some fairly technical things, but they're easy to do. It's very easy to set up this experiment. And it's not part of the traditional geology curriculum. And so there's a new element, both in terms of content and also in terms of the way we do it. But most of the course is computational activities. And again, the idea that we have is for the students to immediately work on real data and authentic methods. So here's an example in the upper left there. There's a traditional map that students see in the textbook. It's being used in another course. And that map is essentially a hand-drawn map made in the 70s and then being propagated in textbooks ever since. And there are more modern versions of a map, and we start with a publication where they made a continuous map of seafloor sediments based on available data. So we have the students download the same data and use the same methods that they do in this paper to create a continuous map. And then we use that as a starting point for other things. So even at 100 level course, these are 5th semester students. It's perfectly fine for them to do authentic stuff. And then the key that I really want to talk about is how we then try to assess students working on these types of problems. And the way we do this is that we have criteria. So we have rubrics with a set of criteria for each activity, and it consists of some very general aspects that recur in many activities, and has to do with, presenting things graphically, some programming issues that occur many times, writing, communication, that sort of thing. And they have the criteria in front of them while they work on task. And then after they hand it in, we give them a report. And the report is auto-generated from the rubrics. And so they know what criteria they will get feedback on. And they don't get a grade on the assignments. They get this report. And we can add individual comments wherever we need. And so here you have examples like, ability to simplify, ability to generalize, things that are not specific to this particular activity, but things that have a much more general applicability. And it's tricky to assess, I think. And so we spend a lot of time trying to formulate these assessment criteria and the feedback, and it's a very difficult thing to do. And the students, of course, are not used to it, and so that adds another layer of difficulty, and we have to be very careful and have sort of a conversational approach all the time with the students, how we do this, why we do it. And they are able to provide feedback all the time and change some of the criteria if they feel it doesn't really match what they did. And they also are invited to propose weighting schemes for different activities. So if something clearly didn't work, too much technical difficulty, they can always do that. Anyway, this is just an example of how we can work in a specific disciplinary content on student learning of something that is general, that cuts across all the disciplines. And working this way makes it easier to see connections with other courses, other disciplines, and to share what we're doing. So we have shared some of this stuff, the rubrics and the assessment reports, sort of the technical parts of that with other courses in the hope that we can improve. Okay, so if we zoom out again, what is it about earth science and the fact that we are dealing with these complex earth systems? What is it about that type of education that mobilizes these competencies that are sought after? So instead of talking about our educational program and our curriculum in terms of all the various components of this system that we want the students to know about, and therefore we have to lecture about them, we should try to identify what is it about working with this type of systems that mobilizes those types of competencies. It's a difficult thing to do, but it's something we have to start doing. And this is the goal of Progress Domain 1, is to assist in this type of, let's say, curriculum development, if you will. And there's some literature on this. So I like this particular figure that I stole from a paper in the Journal of Geoscience Education. And so it tries to do that exercise, to identify what is it about working with complex Earth systems that is generally applicable. And the lens that they're using is the concept of ill-structured problems, okay? Which of course is a very general type of problem, arguably the most general type of problem. So any real-world problem, you know, in science, in the workplace, or in life in general, is an ill-structured problem because you don't have all the information you need. There's uncertainty. There are many ways of doing it. You have to make some choices, and then you have to argue why you did what you did. And in the context of science teaching and Earth system science teaching, working with authentic problems mobilizes a set of key scientific practices. Okay. So it sort of matches the list that several science academies have proposed as sort of key skills, if you will. So you have to ask questions. This is something you have to train to do. You know, using models, producing models, investigating something over time, analyzing and interpreting data, and computational practices are key. So in addition to the components of the problems and the scientific practices that they mobilize, we also have to set up a learning environment that supports that type of problem solving. And some of the key elements there is authenticity, that there has to be a sense that this is a real problem. And students need time to be able to investigate these things. So standard practicals for an hour or two won't really do it. You need more time. And then the difficult, tricky one, which is the assessment, to have an assessment of how you work on these types of problems. And that's tricky business. And the list goes on: collaboration, reflection, all of these things that are sought after as general competencies. And you can see in the middle of this, you find very generic categories like argumentation, which is a key. And again, students, in our experience, when we do our course and we assess them on how they build an argumentation for why they did what they did, it's a bit unusual and unfamiliar to them, and sometimes we get sort of a backlash where they say, well, I'm not here to learn how to argue, I'm here to learn geology. And that's true in a way. And so being able to meet the students in the right way is something that takes practice. And I'm not going to say we know how to do that very well, but we try at least to do this. Okay. Now, one important thing. I've talked to many colleagues about this, and the natural reaction, and I understand it, is to say, well, this is nice, lots of fancy words, but I don't have time to add all this to my course because I already have all this other stuff that I need the students to do. If you want me to add all this, you know, it's going to go on forever. And of course, the point is not to necessarily add things. The point is to be able to see how many of the things we do, many existing teaching activities, even the classic ones, are good examples of this type of activity. It's just that we need to see it, and we need to be explicit about it to ourselves and to the students. So one example, we have one course that runs in parallel with my course, where the students go out on a cruise and they collect sediment cores And before going out, they have to actually make a choice where to collect the core based on other information and work they do beforehand. So they have to make choices. They have to deal with uncertainty, and they have to argue for why they do it the way they do it. And then they collect the core, and they have to work on them in the lab. And so it's an excellent example of this type of problem solving, but it's not made explicit, I think. And the assessment may be lacking. So once they get to the exam, this is maybe not what they're being assessed on in the end, even though they worked on this wonderful problem. So again, it's not about adding lots of new things to courses. It's about recasting what we do in a way that makes it clear to everyone how these are examples of something extremely valuable and can be used in all sorts of settings. And it has implications for the way we talk about teaching. So if we stick with the old categories, you could say that, okay, the activity that they're using, they're going out and picking up the sediment core. That's, it's quaternary geology, or it's marine geology, or sedimentology, or whatever you want to use. So it falls into a category. And if you were to map the curriculum using those categories, it might appear that they're only doing this once in the entire bachelor degree. They only do this once. And so you could lament, they're not going to be good marine geologists or whatever, because they only did this one time. But if we can abstract what they're doing to something a bit more general, it's one example of where they do solve a real world problem and all the aspects that implies. And they do that again in another course. It's a completely different discipline and context, but it's the same type of learning activity, if you will. And then all of a sudden, if we start mapping what the students do in our curriculum from that meta perspective, all of a sudden we can see, okay, there are elements here that recur. We can look at this as a progression, and there's some coherence to what we're doing. And all of a sudden, it's not so important whether or not it fits into a traditional disciplinary category, because those categories will shift depending on who at any given time is a member of the staff and what they're doing and how they're filling their courses with disciplinary examples. So this is something that in iEarth we will try to work towards having a framework for talking about teaching at a more general meta level, so we can see the things we have in common. It's going to take some practice. Okay, this terrible slide that I made at some point was intended to illustrate that iEarth has many focus areas, if we will. We have different domains focusing on students, student learning environments focusing on instructors, employers, external stakeholders, and then of course this backdrop of global challenges that need to be addressed and that our candidates should be able to go out there and work towards solving. And so the point I really want to make here is that having this meta level perspective, and there's a word here or a phrase in red saying competence-oriented curriculum redesign. And that's not a phrase that makes people particularly enthusiastic, but it's essentially what we've been talking about now with trying to keep our focus on a meta level. And that's where we can also see the linkages between these different elements, and that students and employers and instructors and the global challenges can all fit into this framework. And then there's kind of a practical implication of this. There are many frameworks out there in the world for doing competence-oriented curriculum redesign, and we have them at our institutions. We have at the Læringslab here at UIB, we have initiatives, and there are programs already at our university that are doing this and following a set of steps that are supposed to be involved in this. But one issue that I think we can improve upon is the fact that it tends to boil down to spreadsheets with categories. And so we're getting spreadsheets from many levels. We get spreadsheets at the department level, we get spreadsheets from the higher faculty level with categories, and teachers are told to tick off the boxes. You know, are you using collaboration in your course? Yes or no? And that's that's good in a way, but there's a large underlying fundamental problem with it, and that is that something as complex as a curriculum cannot be captured in a flat table. So you would need a very large number of spreadsheets in order to map the relations between the different categories and concepts that are involved. So it's kind of a very basic data management issue, that you have to have a relational architecture in order to capture a curriculum, because there are so many relations between different categories and words and phrases and concepts that you have to have that as a back end before you can even start mapping what you're doing. And here, there's nothing particularly new about any of these things. And we've tried in the iEarth process to find examples of programs, institutions that do this type of thing and that can document to some extent that they have some success in doing so. And it's been a bit tricky, but the examples I have found come from medicine. Oh yeah, it was just my big red "don't use spreadsheets to map a curriculum" slide. It was just to remind myself of saying what I just said. So there is a project in the German medical education that's been going on for some time. And of course, competence oriented curriculum design and mapping is nothing new in the medical sciences or in the professions. So they've been doing that for 100 years. What's a bit new with this particular project is that they highlight the effect of having a relational database architecture and a visual interface. So the ability to immediately visualize this very complex data-rich structure, and for people involved, all the stakeholders, from students, faculties to institutions, and even governmental institutions, to be able to see what's going on from their perspective sort of immediately. I don't have access to this interface, so I've just pulled out a few slightly dull looking graphs from some of the publications. But the point is that you can do a mapping as the curriculum is evolving and is being mapped, both in as fine-grained as at the course level, or at a specific program, looking at longitudinal profiles through a degree, or across partner institutions. So it's a national consortium, and so it's also then a bit analogous to the iEarth initiative. And the key insight that they highlight in these papers is that having this fancy, app, if you will, really got people involved. So showing up at the office of a medical professor and saying you have to, do competency-based mapping or whatever, didn't really work because they said, I don't have time. But having this very easy to use, fancy looking, even though we don't really know what it looks like, interface really got people involved. And so that's a message that I think we can take on board and try to emulate some of the things that they do. Obviously, we're not the medical profession, so we can't use any of these things directly. And this is a German project, so they have this sort of Teutonic database of 500,000 categories or something that they managed to build, and there was hardly any controversy. I think out of the thousands of competencies they had entered into this database, only 2 of them were disputed, apparently. It's kind of surprising to me. So we're going to have to do this differently and at a different scale, but still the concept, I think, is key. And I would like to use an example, since we don't have anything like this, an example of this type of tool, if you will, or framework, as sort of an inspiration. So here's a database that we use a lot in my field. It's the paleobiology database, community-driven initiative. And the whole point is now, of course, this is just a screenshot, so I can't show you the way it functions. But essentially, you can click anywhere on this and immediately get a visual representation of the underlying data, and you can zoom in as fine as you want. And so what I'd like to have you do is imagine that these little entities on the right, there are different taxa, so different fossil groups in this case. Well, imagine that those were the different stakeholders in the earth science education. So we have students, instructors, administration, institutions, employers, and they might be interested in different things. And so they could go down to this colorful bar here and they can say, okay, I'm interested in a specific topic, or I'm interested in a specific program, or I'm interested in specific competencies, and then immediately get access to what is being done in the education in different institutions. And so, for example, if you're interested in, collaborative skills, if that's something an employer really is interested in, well, it's possible then to get an overview immediately. And in principle, we can have students also engage in this type of framework by maybe designing, and this is something they do in the medical profession too, designing progress tests and that sort of thing as they go along. And this is data that could be entered into this database. And in the case of this particular example, this database and the interface is not just sort of a tool that's sitting there. It has changed the way, well, it's changed the whole field essentially. It's changed the questions that people ask. And it's engaged a whole global community. So it has consequences beyond just the technical bells and whistles. And I think something analogous to that we could try to emulate in the educational program. There's a couple of things I wanted to say here that have now slipped my mind. I'll see if I can retrieve them again. Yeah, so for example, when we talk about the earth science educational program and what should the students know and how should we subdivide our program into different entities, instead of arguing about this, so saying, okay, let's use the phrases that we have in iEarth, geohazards, resources, and energy, environment, and climate. Okay, those are words that you know, exist independently of how you choose to teach them. And so they're always kind of relevant, but it doesn't match specific courses or specific research groups in the department. And so people may have difficulty seeing that, okay, well, you know, we could say energy, but energy is just too wide. So you have to say specifically petroleum or whatever. And with this type of framework, there's nothing to argue about, because you can map this structure from both perspectives. There's, you know, you can look at it from the perspective of energy. If you're in the energy industry and you want to know how do students actually work on energy related topics, we can map that, even though specific courses are not called energy. So this, it seems maybe a bit sort of silly to make a big point out of it, but I think it's very important for us to make progress if we can simply allow all of these categories to exist and different perspectives to exist and to be represented in this type of structure. So that's the ambitious goal of Progress Domain 1, is to try to work towards creating something like this, with the goal of helping us to develop a curriculum and to show both to ourselves and to students and to other stakeholders like employers what our education is about. Okay, and I think I'll stop there and